In this video, let us try to understand what is power characterization, and in that we are dealing with static power. And in the next videos, we will be seeing about dynamic power. Here, if you see, power has played an important role in our recent electronic devices like iPhones, iPads, or any electronic gadgets that you pick up. It has something to do with power. We have to store power, and whenever we talk about all these electronic gadgets, where we have all these millions of transistors switching inside the electronic gadget. So we need to control the amount of power that is being consumed by each and every transistor, and for that we need to model the power in such a fashion that is understandable by the designer, so that they can design and control the power supply so that all the devices will consume less amount of power. We have different kinds of powers like static power and dynamic power. So switching power comes under dynamic power. Let us see all these things in more detail. And here remember this one note. These leakage currents will be multiplied with the supply voltage to get power. So we know that the formula for power is equal to V into I. So therefore this leakage power should be multiplied with the supply voltage to get the power. First one, let us see what is static power. So static power is also called as leakage power. The term power and current are used interchangeably. If we make use of these terms called as current, we can reduce real analysis as well as power analysis. So we use these two terms interchangeably whenever required. There are different kinds of leakage powers and they are classified into three types. In that, let us see first one, that is called as subthreshold current. So let us see what is meant by subthreshold current. The term itself tells us that it is something that goes below the threshold voltage of the transistor. We know that threshold voltage means it is the minimum amount of voltage across the gate terminal to form a channel. Let us try to understand with respect to NMOS. So here I am taking N, this is P and this is N. You can call this as NMOS, where here source and body are connected to ground, and we need to apply the potential between gate and source for the formation of channel, and for the flow of electrons we need to apply potential between source and drain. When we apply positive potential at gate terminal, the majority carriers, which are holes in the P substrate, move downward and it leads to the formation of the channel. So the minimum amount of voltage that should be applied across the gate terminal for the formation of channel is called as threshold voltage. And when VDS is greater than 0, the majority carriers, which are electrons, start moving from source to drain, because of which IDS current will flow from drain to source. Let us see what does this mean. So here P, which is positive, so I am connecting gate to positive and source to negative. This is positive, this is negative. So because of this, it leads to the formation of channel. So here channel gets formed, and we need to apply the potential between drain and source. So here I am connecting source to negative and drain to positive. So this is positive, this is negative. So as I am connecting negative at source terminal, the majority carriers in this particular N plus will be electrons. So because of this negative, the electrons which are present in N plus start moving from source to drain. So here electrons start moving from source to drain, because of which current will flow in the opposite direction, which is from drain to source. That's why we are calling this as IDS. Here this is called as VDS, this is called as VGS. So that's what I have mentioned here. Electrons are moving from source to drain, because of which current is flowing from drain to source. That's why we are calling it as IDS. So here I am taking VGS, which is on x-axis, IDS on y-axis. So this is called as threshold voltage. So whenever you are increasing VGS beyond the threshold voltage, then IDS will increase. When you increase VGS, this leads to increase in IDS, but when you decrease VGS below subthreshold voltage, the current does not vanish completely. It takes some amount of time for the transistor to turn off completely. So whenever you are reducing the potential below threshold voltage, it takes some amount of time. So this is called as some threshold voltage. So less than threshold voltage means this portion. So whenever you are reducing VGS below threshold voltage, it does not vanish completely. Why? Because it takes some amount of time to vanish completely. Why? Because some amount of electrons will be present in the channel, because of which there will be some amount of current called as subthreshold leakage current. So during this time, there exist electrons which are present in the channel between source and drain, which causes subthreshold leakage current. So whenever you are reducing VGS below threshold voltage, there will be some amount of electrons which will be present within the channel, because of which it leads to some amount of current called as subthreshold leakage current. This happens when the gate terminal is at static 1 or static 0, that is, which is below the threshold voltage. So this is about subthreshold leakage current. Now let us see some more points in detail about subthreshold leakage. The subthreshold leakage depends upon threshold voltage of the transistor. For example, higher the threshold voltage, lesser is the subthreshold leakage current. If threshold voltage is more, then obviously leakage current will be less. Note, if the threshold voltage of the transistor is more, then delay of the transistor increases. Why? Because it takes more amount of time for the switching. Lower the threshold voltage, higher the leakage current, but delay will be less. Why? Because it will be switching very fast. If threshold voltage is low, then switching will be faster. So obviously delay will reduce. So because transistor takes less amount of time to turn on. So that's why here delay will be less. Whereas higher the threshold voltage, lesser is the leakage current, but here the problem is delay will be more. Why? Because the transistor will take more amount of time to turn on. So this is the difference between lower threshold voltage and higher threshold voltage. Simply, if threshold voltage is less, the transistor will be switching very faster, but the problem here is we'll be having higher leakage current. Whereas if you are going for higher threshold voltage, the transistor will take more amount of time to switch, therefore obviously delay will be more, but here there is no problem of leakage current, but switching will take more amount of time. So check this example here. I am taking some random VT1, this is the lower threshold voltage, some intermediate threshold voltage and higher threshold voltage. Because of these threshold voltages, we'll get subthreshold current. So if you take VT1, here switching will be faster, but the problem here is leakage current will be more. This is higher threshold voltage. Here leakage current will be less. But the thing is the transistor will take more amount of time to turn on, because of which delay will increase. Whereas here delay will be less. Simply you can treat this as LVT, this is HVT, this is RVT or SVT, regular threshold voltage or standard threshold voltage. So that's what I've given here, lower threshold voltage versus higher threshold voltage. So VT1 is lower threshold voltage, VT3 is higher threshold voltage. So see here, when VGS is more, IDS will be more, but when you reduce VGS below threshold voltage, there exists some leakage current. Why? Because the transistor takes some amount of time to completely turn off. So it won't turn off immediately, because of which we get some amount of leakage current. But the advantage with smaller threshold voltage is that the transistor turns on quickly, so delay will be less. So for LVT, leakage current will be more, switching will be faster, and advantage is delay will be less. Now let us see for higher threshold voltage. When VGS is more, IDS will be more. Now when you try to reduce the VGS, that is when you come below the threshold voltage, the transistor turns off and there won't be much leakage current. The problem when threshold voltage is more is that it takes more amount of time for the transistor to turn on, so delay will be more. So this is about HVT. HVT leakage current will be less, switching will be slow and delay will be more. So we have to choose threshold voltage somewhere around VT2 to compensate these problems. So if you are going for lower threshold voltage, we are getting the advantage like delay will be less, but in HVT delay will be more. Suppose if you are focusing on leakage, then if you are going for LVT, here leakage current will be more, whereas here leakage current will be less. So you have to choose somewhere between regular threshold voltage or standard threshold voltage. Now second one in terms of static power is junction leakage. So just now we have seen subthreshold leakage, and the next kind of leakage is junction leakage. So you can understand this junction leakage by means of this example. Here we are going with an example of NMOS. So here I am using NPN. So here source and body. So this is source terminal, this is body terminal. They are connected to ground. And generally these junction leakage exist between this drain terminal as well as the substrate. Why? Because here this is positive, here this is negative. As we know that whenever we are joining one P substrate with N substrate, there will be formation of some depletion region. If I am joining one P and N, there will be formation of some depletion region. So here also the same thing comes into the picture. So here there will be formation of some depletion region, and because of which there will be some amount of junction leakage depending upon the potential that we are applying it. source, gate and drain terminals. So here this portion is called as area of source, this is area of drain, and for the formation of channel we know that we need to apply a potential between gate and source. So here this will be connected to negative, this will be positive, and for the flow of electrons here we need to connect negative, this should be positive. So this will be VDS, this will be VGS. Now here, depending upon these potentials, we need to see whether this particular diode is becoming forward bias or reverse bias. So we know that for forward bias, this positive, this is negative. If positive is connected to positive and negative is connected to negative, it will be forward bias. Similarly, if a diode, this is P, this is N, if positive is connected to negative and negative is connected to positive, then it is called as reverse bias. So this is reverse bias, this is forward bias. Simply you can treat this as P, this as N. Now depending upon this, we will see whether this particular diode is becoming forward bias or reverse bias. So you can see here source is connected to negative, and again this is again connected to negative with respect to VGS, this is with respect to VDS. So if this is negative, this portion will be negative and drain is positive. So if you see here, this is negative, so that's why I am taking N here, and here P substrate is positive, so this is P. So simply this is P, this is N. If P is connected to negative and N is connected to positive, so it is something like this: PN, P is connected to negative, N is connected to positive. So this will be reverse bias. So see here, there will be formation of reverse bias PN junction diode between diffusion and substrate. So there will be a flow of reverse bias leakage current between diffusion, that is drain, and substrate. This is called as junction leakage current. So because of reverse bias, there will be flow of some amount of leakage current, and because of this we are getting junction leakage current. Junction leakage current depends on number of facts. It depends upon doping concentration of N plus region, that is source or drain diffusion regions. So it depends upon the doping concentration. So simply doping is nothing but adding of impurities. It depends on the area of source and drain diffusion regions, that is more area, more doping and more reverse bias leakage. It depends on doping level of substrate. Generally P-type, that is substrate, is lightly doped compared to N plus regions. It depends upon diode voltage levels. So this is all about junction leakage. So simply junction leakage exists between drain and the substrate, and it depends upon the potential that we are applying at source, gate and drain. So because of this reverse bias diode, we are getting this kind of leakage current called as junction leakage current. Till now in static power, first one we have seen subthreshold leakage current, second one we have seen junction leakage current, and the last one is tunneling current, which is also called as gate oxide leakage current. So now let us see this one. This is the current that flows from the gate terminal through the oxide into the substrate. So it will be flowing like this from the gate terminal through the oxide. Here oxide is SiO2 into the substrate, into the P substrate. So take this example. So N, this is P substrate. So again I am taking example of NMOS only. So here this is a current because of tunneling from gate into the substrate through oxide SiO2. So free electron levels is the energy level at which electron is free to move. They are placed at different positions because of their energy level. So generally metal is nothing but a conductor. So here I am using polysilicon, or else it can be metal. Polysilicon, or else it can be by aluminium also. So this is a metal. Next one is oxide, which is an insulator. Here it is SiO2. And semiconductor, here semiconductor is nothing but a substrate which is of P-type. So in static power, till now we have seen these three things. We know that static power is also called as leakage power, and this three comes under static power, that is subthreshold current, junction leakage and tunneling current, which is also called as gate leakage. Here these first two are comes under intrinsic leakage power, and the third one is called as gate leakage power. Now let us see first one, what is intrinsic leakage power. So here the attribute leakage underscore current is used to represent static current within the dot lib. Make sure it should satisfy KCL, that is Kirchhoff's current law, that is sum of current entering is equal to sum of current leaving, or else simply if you add the entering currents and leaving currents, it should be 0. So if this is a leakage current, here the above portion you can treat it as positive, bottom part you can treat it as negative, and this point is called as an origin. When you add this above positive and negative, it should be 0. So let us see what is leakage current. So leakage current is the attribute that is used in .lib. This is of CCS power format, that is composite current source. So you can take the example of this .lib snippet. So suppose cell, name of the cell is my_d flip-flop, and leakage current and when condition. When condition means here I am taking two inputs, D and clock. So if two variables are there, we get four combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. So for each and every combinations we get value. So this is state dependent current. When D is equal to 1 and clock is equal to 1, you will get four states like this. So depending upon the when conditions, we will get the value. So you can see here PG current with respect to power VDD. So the value is 209 nanoamperes, and PG current with respect to ground, that is VSS, value is minus 210 nanoamperes. Here this value is I static. These are static current values. So this is the static current value, which comes with the attribute called as leakage underscore current. So generally, if you add these 209 nanoamperes and minus 210 nanoamperes, it should become 0. But it is not coming as 0. Why? Because there will be some amount of fluctuations that will be happening within the circuit. Now let us see what is leakage power. So till now we have seen leakage current, that comes under composite current source format. If it is leakage power, we know that power is equal to V into I. So simply multiply this I static current with respect to supply voltage VDD, so that we get power. So simply I am taking some example of VDD as 1.8 and static is 210 nanoamperes. So simply if you multiply these things, we will get power as 378 nanowatts, or else you can write it as 0.378 microwatt. And this units we need to specify within the .lib. So depending upon the .lib format, we will get this power as well as current, voltage, resistance, capacitance and all. Remember this point, leakage power falls under NLPM, whereas leakage current is coming under CCS. NLPM means non-linear power format, whereas CCS means composite current source. So see the example here for a cell of D flip-flop. Here leakage power for when condition D is equal to 1 and clock. Here we are getting value as 0.378. Here leakage power unit is in terms of microwatt. Next one, let us see what is cell leakage power. So this comes under NLPM format, which is non-linear power modeling. So example here is AND gate. Here leakage power when A is 0 and B is 0. This is a value. This is A 0, B is 1. This is the value of leakage power that we are getting. When A is 1, B is 0, this is the leakage power value. And when A is equal to 1, B is equal to 1, this is the leakage power value that we are getting. As we have seen, leakage power is equal to V into I. So simply VDD should be multiplied with I static, so that we get this particular thing. And it depends upon the number of variables. As we are going for AND gate, which is of 2 input AND gate, which will have 4 combinations. So that's why we are getting 4 values here. Now let us see how to calculate cell leakage power. So simply cell leakage power is average of all leakage power. So simply you add all the leakage powers divided by number of states. Suppose if you are going for 3 input AND gate, then you will get 2 power 3, 8 different combinations. So add all the leakage powers and divide it by 8. Then you will get the cell leakage power. So this is the cell leakage power that I am getting, and it should be positive. Last one is gate leakage power. So gate leakage power, it comes under CCS power format. So here I am characterizing this particular NOT gate, and this is a driver. So here pin name is A, input is A, output is Z. So here I have mentioned this is a cell that needs to be characterized. So cell name, leakage current when A is equal to 0, and gate leakage current, I mean gate leakage Z. So input low value, input high value. So let us see how we are calculating this one. The current which is entering the cell that needs to be characterized is treated as positive. The current which is leaving the cell that needs to be characterized is treated as negative. Means in this, if anything that is entering into the gate is treated as positive, and the thing that is coming out of the gate is treated as negative. So simply entering is treated as positive, coming is treated as negative. So entering is positive, coming out is negative. So take this example. So initially I am applying 0 here. If it is 0, this is PMOS, this is NMOS. So PMOS will be on when input is 0, NMOS will be on when input is equal to 1. These are on conditions. So as I am applying 0 here, this is on, this will be off. As this is on, this VDD will be connected to output. So here I am getting VDD, I am taking it as 1. Now this 1 will be applied at here as well as here. So 1 for PMOS this will be off, and 1 for NMOS this will be on. So that's the reason there exists a path from this to this towards ground. So in this manner, this one as well as this one gets turned on and it will be connected to ground. So here if you see, the current is entering the cell that should be characterized. So here this is a cell that needs to be characterized. As here it is entering, this should be treated as positive. So current entering the cell to be characterized should be positive. Next, second case, when I am applying 1 here, so 1 for PMOS, this will be off, this will be on. If it is on, it will be connected to ground, so I am getting output as 0. Now the 0 applied to PMOS as well as NMOS. So here this will be on, this will be off. So there exists a path in this manner. Here this will be on and here this will be on. So here if you see, the current is coming out of the cell to be characterized. This is a cell that I am characterizing, and here the current is coming out of the transistor. So here current leaving the cell to be characterized should be treated as negative. So this is the meaning of current entering and current coming out of the cell to be characterized. So input low value means 0, input high value means 1. It depends upon the potential that we are taking. So this is all about power characterization, and we have seen only static power. In that we have seen what is subthreshold leakage current, junction leakage and tunneling, and we have seen different attributes like leakage current, leakage power, cell leakage power and gate leakage power. So remember these things. So leakage current falls under CCS, leakage power falls under NLPM, cell leakage power falls under NLPM, gate leakage power falls under CCS, composite current source and nonlinear delay model. These two are present, NLDM, CCS. If it is NLPM, it is nonlinear power modeling. So this is about static power in power characterization.